Good day, and welcome to this present demonstration of Tunnel Plus, the module for the definition of the luminance curve at the entrance of straight road tunnels of our program, LISTA 4D. So, if we want to define the lighting of a tunnel using LISTA 4D, you have two different approaches. Through these two icons, you have the wizard for tunnels approach and the advanced project for tunnels approach. These two approaches are different because for the wizard, we can define few parameters. We can define a simple configuration with a single luminaire, and then the program will help you to define the tunnel. Through the advanced module, you can define the tunnel through different steps, which is a longer process than the wizard project, than the wizard approach. But it gives you a wider freedom to define the different section of the tunnel. So, for example, not only the carriageways and the sidewalks in case, like with the wizard, but also parking lanes, emergency lanes, etc. So it is a lighting design at an higher level than the wizard. So let's start with the wizard. And let's say that through the wizard, it is possible to define what is constant in the lighting of a tunnel. So the lighting of the permanent zone of the tunnel, where we have usually a single luminaire with luminaires at the same interdistance and with the same characteristics. So through the first window appearing, it's step one. We have to define the grid. We have to select the standard. So, for example, we select the standard about Europe, for example. This is the European standard. And through here, the program automatically configures itself in function of the parameters to manage. So, for example, in this case, selecting the European standard, you have a fixed number of points, transversal points for the calculation. Let's say that in case of selecting free means that you have all the parameters editable. So it means that you can configure the tunnel as you want. And also considering some standards that are not considered at our program for the time being. So let's go back to the European standard. Then you may define the observer's age, but let's say that usually, coming from my experience, we do not have usually to change this one because it is widely accepted the reference of an eye of a guy with 23 years old. Then we have to define the observer type. So if it is a moving observer or if it is a fixed observer. The difference is very simple. If we consider the fixed observer, we have an observer which is placed 60 meters before the first line of the calculation grid. But then the other points are kept at the same interdistance, and so having the fixed observer, the other points are, in case the first and the second have an interdistance of 2 meters, then the distance in between the observer and the second line of points will be 62. And the program will consider only 100 meters, an area of 100 meters. Let's say that it is a nonsense if we have a tunnel of 3 kilometers and we have the observer always placed at 60 meters. So we defined through our program to consider at the first step a section of 100 meters And then we will move the observer to the second area of 100 meters and have the observer with the same reference to the second area. So if we have a tunnel of 3 kilometers, for example, we may have the calculation repeated 30 times. In the case of the moving observer, we have an observer which is no more placed at the distance of 60 meters to the first line of calculation points, but it is placed at minus 86 meters. But then the observer is moved. So, for example, if we calculate the first step is to calculate the first line of the transverse points of the calculation grid. Then you move to the second one. The observer will move forward of the same interdistance, so that the distance in between the second, third, fourth line of calculation points, transversal points, will be always kept at 86 meters. Next step is to define the carriageway data. So in this case, we define the carriageway, the single carriageway, or two symmetrical or two asymmetrical carriageways. What is the difference? The difference is that in this case we have a single carriageway, like the one, for example, of a tunnel, of a motorway tunnel, where you have, for example, 2 or 3 lanes at the same carriageway. Whenever we consider two symmetrical or asymmetrical carriageways, we consider a tunnel which has a median in the center, so it's open. It's not the case to consider two tunnels with two different directions. This is not the case of the program. So let's repeat. It is only a tunnel, a single tunnel, with two carriageways separated by an intermediate, and that's it. So it's, repeat, a single tunnel. And whenever we select the carriageway, we can select if it is a one-way, so that the drivers are running along the tunnel in a single way, in a one-way, or in 2 ways. Then we have to define the geometry of the tunnel. So as a default value, the program is proposing 1.2 meters for the sidewalk A and the sidewalk B, and the total carriageway width at 7.5 meters. But it's clear that, as you can see, it is possible to change exactly to the width of your tunnel. In here, we define the number of the total number of lanes. Then we define the lighting class coming from our standard. Let's say that in the program, in the tunnel module, it is not necessary to define this class. This is the class of the road outside the tunnel, so that it is possible to define a relation in between the class outside the tunnel and the class inside the tunnel. But this is not managed by the program. So you can define for your purpose the class, but it is not used by the program. What is used by the program is the R table, so the reduced table of the reflection coefficients of your asphalt, of your cement, and the Q0 factor, which is corresponding to the parameter defining the reflection property of your surface. In this case, we say that the surface is reflecting a 7% of the total light coming to the asphalt, coming to the cement. Next step is to define the arch. So it is defined to select the section of your tunnel. We may have different sections in function of the different states because, for example, this tunnel is not so frequent over here in Italy. This one is very frequent, but let's stay with the cube, let's stay with the rectangular section of a tunnel. At your right, you have the related parameters. So in this case, we have to simply define the width of the tunnel and the height of the tunnel. In here, we may say that it is a tunnel with a 6 meter high height. And the width is defined over here, the WT. So as you can see, the program is proposing 14, so it is possible to have a wider tunnel than the carriageway and the sidewalks, because if we sum here, we have 9.9 meters, and the program is proposing 14. So this is in case you need something more, and you have an area where you may add whatever you want. But if you select auto, then the program is placing here exactly the sum of the sidewalks and the carriageway. Then the active wall. The active wall is the wall considered as an important part of the lighting of the tunnel. And so usually it is a 2 meters high. So for example, over here in Europe, we consider 2 meters high, and we calculate at a height of 1 meter and at a height of 1.7 meter. And for this wall, active wall, we have to define the color. So we simply click on this section, and we select the color of the wall. So for example, we may leave this color, and automatically the program is proposing the reflection property. So in here you have to input the value that is maybe supplied by the client. So let's say that in here we have a 50% reflection. What is the ceiling color? The ceiling color is not only corresponding to the ceiling of your tunnel, so this part, but it is considering the cavity. So from the active wall, in this case 2 meters, up to the top. So we consider it has a ceiling color, also the wall part that it is above the active wall and coming to the top, coming to the ceiling of the tunnel. In this case, so double click, we select this color, and we say that we have a 25% reflection. Let's say that in any case, whenever you run a calculation, the luminance calculation on the surface, on the carriageway, it is usually not so much affected by the reflection of the walls due to the system that we use for the lighting of the tunnels. Okay, once we have finished, we come to next, and we define now the geometry of the luminaires. So where we want to place the line of luminaires. We have luminary distribution to select, so one row on the right, one row on the left, two opposite rows, two staggered rows, or one row suspended at the center of the tunnel. Let's select one row on the right. Then we have to define the position of the luminary in relation to the edge of the carriageway. We consider the edge of the carriageway because at the beginning, when we started to develop the programs, there were no sidewalks. And so the reference was taken to the edge of the carriageway. And this was kept because our customer were used to work in this way. So the first step is to define the edge corresponding to the carriageway. But then you will see that the program will automatically consider also the sidewalk, because the reference will be placed here. So at the end, having a sidewalk of 1.2 meters, if we define 0.5, then the position of our luminaries related to the absolute axis will be 1.7. Then where we want to put the luminaires in the height. So let's say that we have a 4.5 meters. The spacing interdistance in between two consecutive luminaires, let's say that we place it at 3.5, and the tilting. So the tilting and the rotation and the tilt angle along Y was very used in the past because we had luminaires that were using only sodium lamps, and it was not possible to be so flexible like we are nowadays with the LEDs and with the lenses that we use for the lighting of the tunnels. So in this case, you having to use now LEDs more and more, we can say that we can leave the luminaire perfectly horizontal, so with the glass horizontal to the plane, and so we do not consider the angles. In the past, these angles were particularly used. So now it's the time to select the luminaire. So we have different options to select the luminaires through a folder where you have your LDT, IS, or Excel files, different file formats we can manage, or through the most used catalog you have right here at your right, or use the catalog of the program, the database of the program, which is the ListWin. So let's use the folder, and let's consider this luminaire for the permanent lighting. We simply drag and drop, and then the luminaire will be uploaded. And now we are ready to run the calculation in function of the parameters that we have defined so far. We come to calculation, and we do not consider the direct indirect component because, as we said, it is not affecting the lighting levels so much. And the calculation will be much faster because we can reduce, if we do not consider indirect, then we can reduce to 0 the resolution, the accuracy. And as you can see, the calculation will be much, much faster. So we did, I did an error because now the tunnel is only 35 meters long, as you can see here, because I didn't tell you what it is, the calculation area data definition. So for example, in here you can define the length of your tunnel. In this case it is 35 meters, but we want to have it at 200 meters. As you can see, automatically the program is considering a total number of 571 points, which means that roughly we have a point every 35 centimeters, which is quite a great deal of points. If you do want to change this number of points, you can do that, and let's say we can place a total of 200 calculation points in the longitudinal way. So we go back to the calculation and we repeat the calculation. The calculation time will be a little bit longer as we have a larger number of points, and in here we have the results. As you can see, the value is pretty much, because with the M1 we consider it as a class, we may consider a total of 3 candela per square meter inside the tunnel, or 2 candela per square meter. So what shall we do? We have two options. We go back to the tunnel definition, and we may change, for example, the interdistance, and we put it higher, at a higher interdistance, higher value. And in case, we may also dimmer the the lighting. So if we want to keep the same interdistance, we may reduce the flux emitted by the luminary using the dimmer, because we may say that we have a sort of dimming with the LED luminaires using managing the currents, the driving currents. So using the dimmer, this is possible, but it has to be done in the proper way, because the 100% of the dimmer means that we are regulating at the highest level of the current. But then we must know which is the lowest level, the minimum level of the current, and which is the corresponding flux, in order not to calculate with something, with a flux that is not allowed by the luminary itself. In this case, we will see later on that it is possible using Leicester to manage directly with a single file the driving currents of a luminary. So let's say that now we reduce this one to 50%. So we may use the cursor, or we may write here 50%. And now we go back to the calculation and verify if it is okay or not. So we are a little bit above the 2 candela per square meter, and let's say that it is okay. So we close the window and we get back to the project. And we may say that the parameters defined so far are enough for the permanent lighting. And now we come to the definition of the lighting of the entrance zone and the transition zone, where we must have an higher level of lighting compared to the permanent zone. So once we come to the step 2 window, we have over here access to the advanced project. So this window will appear. Here now we are at the advanced section. As you can see, the program was able to define the different section, the different parts of the tunnel. So the sidewalk A and B, the carriageway, etc. Through the program, it is possible also to add other sections. So for example, if we want to add a new section, we may place the cursor over here at the table wherever we want to add the section, and the program will include the section in between. So we may have another lane, we may have an emergency lane, a parking lane. So it is we have a quite high range of options to define, so that you can complete your tunnel through the advanced module. Then it is also possible to manage the luminaires over here, but we come to this point later on, because now we access the real Tunnel Plus module, which is the definition of the luminance curve at the entrance of the tunnel. So once we select the luminance curve, this window will appear. And through this window, we can define the name of the customer, we can define the tunnel name, and down here, we define the standard that we want to apply in order to define the luminance curve. Because so far we have used all the definition of the road. Apart from the definition of the reflectances of the tunnel, we didn't define any other parameter besides the one defined at the standards for the lighting of roads. And only this one is related to tunnel lighting, so the definition of the luminance curve. So let's select the standard. We select CIE 88. These are standards coming from Italy, and this one is from the European Union. This is the technical report issued by the European Union. And this one is the standard from Spain. So let's select the CIE 88. And as you can see, the program configure itself in order to let you input all the parameters related to CIE88. Once we select CIE88 version 2.04, okay, let's say that it's now on the process, the development of the new CIE88 standard recommendation, and probably it will be available probably during the end of the year, before the end of the year, or next year. The process is running. So whenever you select the CA88, you have two options in order to define the luminance at the entrance of the tunnel. So through the Adrian, with which you can define at the end the threshold luminance, or through the L20 method, which is the old method, and I will tell you later on what is the difference in between these two methods. So over here, we have to define if it is a long or a short tunnel. So we say that our tunnel is 200 meters. So if we cannot see the exit, it should be considered as longer. Otherwise, it is a short tunnel. Let's say that it is, in this case, it is a long tunnel. We have to define the speed. We have to define the slope. So why it is important to define the slope? Because if we are, the slope is at 0 degrees, it means that we are running, we are driving on an horizontal plane. And the program will calculate in function of this the stopping distance. But if we have a slope, a negative slope, so it means that we are going down. And so it means that in order to stop our car, we need a wider space than with the 0 slope, with the horizontal plane. On the other way, if we have a positive slope, so let's say +1 degrees or +5 degrees, it means that we need a lower distance in order to stop our car. So the slope helps us to define carefully the stopping distance. Then the speed, it is an important part of the program, because the speed with which you access the tunnel, it is allowing you to define a longer or a shorter interdistance, stopping distance. Then the direction of your tunnel. If you are driving northward, it means from the south to the north. It makes a big difference in case you consider this one, or in case you consider east-west. In a flat area or in a mountainous area, there is a big difference, because in this case, with a tunnel in a flat area, it means that maybe you have a wider part of the sky that is affecting your eye, because it has a much higher luminance than, for example, the vegetation, the meadows you may have. So, for example, in a mountainous area, you have the mountains that are shielding, that they are covering the sky, and so the luminance at the end will be lower. So let's say that we stay with a mountainous eastward tunnel. And then we have to define the type of installation of the luminaires. So you have three options: the pro beam, the symmetric, and the counter beam. The pro beam is, we can say, I do not know any tunnel lighted in a pro beam system. It means that if you have an asymmetric luminaire, the asymmetry is going the same direction like the driving direction. In the case of the symmetric, we have a luminaire that is spreading light in equal way in the two directions, in the pro and in the counter direction. And the counter beam, it is vice versa compared to the pro-beam. So it means that the beam, the asymmetric beam, is going in the opposite way related to the driving direction. The counter beam showed to be the best solution, because as you can see, the beam is lighting the carriageway, and the light is coming in front of the driver. So whenever you access the tunnel, you have the carriageway that is well lighted and the obstacle in front of you. So the car that may be in front of you, the back part of the car, it is not lighted. So you have a good contrast in between the car and the surrounding, corresponding to the walls and corresponding to the carriageway. Running the calculations through the different systems, it was clear that the counter beam system, it is the best solution in order to give a very high level of luminances, which is what we need in order to have the proper lighting of a tunnel. Then we have to define the carriageway conditions. And the carriageway conditions means that we have two options, wet and dry. Let's consider dry. Over here, you can see that coming from the parameters that we have defined so far, it is possible now to have a stopping distance of 62.8 meters. But in this case, as you can see, it is also possible to define a stopping distance by the user. So without taking into consideration the parameters defined up to now. Over here, we have to define the traffic flow. So how many vehicles per hour? Let's consider 1,000 vehicles, and the direction, one way. Okay. Over here, we have to define the veiling luminance. So the luminance that we have coming from the atmosphere. If we have a foggy atmosphere, it will affect our vision much more than without having a foggy atmosphere in between us. So in between the driver's eyes and the entrance of the tunnel. It is clear that if we have a high veiling luminance, then we need which is disturbing our vision. We are going to have a higher level of luminance inside the tunnel. This veiling luminance, we can say that it is not the same all over the year. So you have to consider what is the worst condition that you may face approaching the tunnel. As you can see, the atmospheric luminance coming from the definition of the veiling level, it is changing in function of your selection. So let's say that we have a very low veiling luminance, so that the atmospheric luminance will be 100 candela per square meter. Now we come to the definition of the luminance curve. So for example, through the analysis of a photo of the entrance of the tunnel, through a fixed value. So for example, your client is proposing you, so the luminance at the entrance, I want that it is at 150 candela per square meter. So you simply input here the value, and once you input the value, automatically the program, in function of the defined parameters, will draw the green line, which is our luminance curve. The other option is the fixed curve. So your client may supply you the value, and then the program will automatically define the curve, as we see up to now. Or you may input here, your client may supply you, for example, an Excel file with the meters, the progressive inside the tunnel, the X of the tunnel and the corresponding luminance value. You input here and the program will automatically draw the curves. So in this case, let's say that the interior luminance means the luminance at the permanent zone in function of the defined parameters, it is 3.29 candela per square meter. But let's come to the case of the photo. So the photo means that, as we saw, we have two options. The first one is through the Adrian, which is the system that replaced, and let's say in some cases replaced, in some other countries they said no, using the L20 it is a much easier system than the Adrian's one, and so we stay with L20. So it's up to you to use one of the other. I may say that L20 is less precise than Adrian. So let's analyze the Adrian approach. Once you select the Adrian, you come to image, and from here you have to select, at the first step you have to select the image you want to use. So you select this option, insert image, and from the folder you select images, and we select this one. As you can see, automatically the program is adding the Adrian's diagram on the image, but it is clear from this image that the point, it is not exactly the point, the center point of the Adrian's diagram. It is not exactly at the center of the tunnel. So you may move it simply clicking with your right click of your mouse, set center, and so as you can see, the center was moved to the proper position. The second step is to define the width of your tunnel. So always right click, set first measurement point, and right click, set the second measurement point. As we know, it is 9.9 meters. So, okay, we zoom with your mouse, and as we can see, it was not perfectly defined. So we go back and we define set first measurement point and set the second measurement point, 9.9, okay. And now it is perfectly defined, but as we can see, this point, which should be on this point at the center, it is not perfectly placed. So we have to move it a little bit down, set center. And now we can say that it is perfectly placed. Okay, and so now we define the weight of the different sectors of the Adrian's diagram. How can we do that? Yellow tips, superimpose data, and a click of the mouse. So first of all, we have to define the sky. So we select sky, and we simply click. As you can see here, it is not completely 100% sky. So we may right-click of your mouse, values, and we may define that it is 90% sky and 10% meadows, and the two values will be displayed. In this case, again, it is not completely sky. In this case, we may say that it is 30% sky and 70% it is meadows. Now we move to, okay, this one is sky, this one we may consider as sky, and this one is again, let's say, as you can see, it is always more or less. It is not a calculation, a perfect, let's say, calculation, and 70% metals. Now let's come to metals, and we select the metals. In here, we may say that this one is metals, and rocks. This one could be rocks, like this one, for example. We go back to this one with metals, and now we come to the road. We no more define so perfectly as we did before. Okay, and now probably only the entrance, the portal, should be defined. So again, one, and this one. Okay, let's say that we have finished, and now we are ready to draw the curve, the luminance curve. So we select curve, and we see over here that something is missing. So I didn't define all the parts of the tunnel. So I can see that here something is missing, this one is missing, and the other one is road. And let's go back. And now the program design the related luminance curve. The green one, which is the curve giving the minimum value that you shouldn't go be underneath this curve in your lighting design. What is the blue line? The blue line is a line that was added at the Italian standard for tunnel lighting. Why? Because whenever you have a lighting level which is above the green line, it is good. But being above means that you may be at the entrance at 140 candela per square meters, but it is good also if you are at 240 candela per square meter. So CIE 88, it is not giving you the maximum level, so it is not energy saving. So this curve was introduced by the Italians in order to be the energy saving limit. So your calculated luminance curve shouldn't be above the blue line and should always be in between the green and blue curve. Okay, that's it. Let's say that in what is the difference in between the Adrian's approach and the L20 approach? So I said before that it is a less precise method. Yes, it is less precise because you upload over here the image as we did up to now, and you simply define more or less what is the weight of the sky area, the weight of the road area, the rocks area, the building area, the snow area also, and the meadows area. As you can see in here, the portal is missing. And so the sum of these six figures shouldn't be 100%, because otherwise you won't consider the portal, so it is a nonsense to run the calculation of the luminance curve. So as you can see, it is much less precise than the Adrian's approach. And so, but in any case, it's up to you to use one or the other method, also in function of the standard you apply in your countries. So once we have finished we close this window. We close this window, and we are ready now to add the luminaires in order to correspond, to have the lighting corresponding to the luminance curve we have defined up to now. So, for example, in here you can insert a new line. Usually, I simply do in this way. I may select another luminaire from here, and that's it. So, for example, a floodlight, like in this case. Once I confirm the luminaire, which is the first line, let's say that in here we write permanent. Over here, we may say reinforcement 1. And so this is one approach. The other approach is to copy the permanent, and then you change the luminary. In this case, it is not needed to access the catalog we have seen up to now. So if we want to replace this luminary using this one, for example, I simply open the folder and I drag and drop the photometry into the program, into the window. Now we have this line of luminaires, which is based on a total of 5 luminaires. We can run a simple calculation. So, for example, in this case, in order to start exactly at the 0, we start at, so for example, 3 meters. In this case, we start at 5 meters because in this case we have an symmetric luminaire. In this case, we have an asymmetric luminaires. So we place it, let's say, in the middle of the tunnel at a height of 4.5 meters, and the total number of luminaires, let's say that we have a total of 3 interdistance. The interdistance of 2 consecutive luminaires is 3 meters, and we want to come to the total area, which is, let's go back for a second, so because I didn't show you one main point. Over here we have the curve, and as you can see here, coming from the CIE, we have 3 different sections. So the entrance section, the entrance zone, which is based on 2 parts, the constant one for 50% of the stopping distance, and the other 50%, it is a variable zone, but it is linear up to the point of 40.7% of the luminance value. And then this is the transition. This is the transition zone. So we have one zone which is constant for the entrance again, but variable, and then the transition zone up to a little less than 320 meters, as you can see here. So in this case, we consider that we have the constant lighting up to little less than 40 meters. But if you consider the asymmetry of this luminaire, it is clear that you have to place it. So we said a little less than 30 meters. We place the section length at 40 meters. With an interdistance of 3 meters means that we have to add 14 luminaires. But this luminaire has a total flux in this case of roughly 20,000 lumens with a current of 0.5 amps. But having this product, the curve of flux and power in function of the current, we may access it and we may say, let's start at the top. So we move it at 0.75 amps. We confirm, and now the flux it is higher. So once we come to this configuration, one main point we have to consider, that in this case, as you can see, the asymmetry is along the C90 half plane. So it means that it is a photometry that was done considering a road lighting luminary, where the 90 is transversal to the direction of the tunnel, to the axis of the tunnel. So it means that if we want to aim properly the luminary, we have to rotate it 90 degrees. So if we come to finish, then the luminaries were headed, and if we visualize the photometric solid, we can see that it is properly done, because as you can see, the luminaries, the asymmetric luminaries, are spreading the light exactly in a counter beam way. So now we go back to the calculation. And once we've finished, we can analyze the results. As you could see before, there was only one section, the permanent section. But in here now, the program is splitting the different zones and analyze the calculations, analyze the results in different ways in function of the zone. Because if we have a constant zone, we can measure the overall uniformity of the area under consideration. But if we have a variable zone where the luminance is variable, then it is nonsense to consider the overall uniformity. So in this case, you have to consider the transversal uniformity. So as you can see here, we have a threshold zone, the first half, which is constant luminance, and we have the overall uniformity, which is quite good, with a quite high luminance, but it is not corresponding to the needs. So the luminary we used is giving us a quite interesting uniformity, but it is not so powerful to reach the roughly 120 candela per square meter that the luminance curve is proposing us. So what can we do in this case? If we have to go on working with this luminary, we have to go back. We go back to the project and say that in place of an interdistance of 3 meters, we place an interdistance of 2 meters, and we move this one to 2.5, and we copy this row of luminaries. We duplicate and we place it let's say at 5.5 meters. Much better, 6.5 meters. Always 14 luminaries. And we go back to the calculation. As you can see now, we have 2 rows of asymmetric luminaries. And we start. And we go back to analyze the threshold, the first half of the threshold. We are at 85. Not so far, but it is not yet enough. But in any case, if we select this one, we can have also a graphical visualization of the results through the selection of the luminance curve, where we are going to have, as you can see, we are going to have the calculated curve which is this black one, and the reference, which is the green curve. In this case, reading this diagram, we have an information that, for example, the total number of luminaires, the 14 luminaires that we had, are not enough to reach this value. So we have to increase the number of luminaires for the first half of the entrance zone, at least up to 50 meters. So we may go back, modify from here, luminaires, and so we said that in place of having a section of 26 meters, we must have a section at least of 55 meters. And so the total number of luminaires is now much higher, is double than before. We run again the calculation, and then we go back to analyze the results. And step by step, so as you can see, now we are pretty close to the final result. So we select this one, we go back and select luminance curve. As you can, so now it is pretty much. So one by one, applying the changes one by one, you can come exactly to the point, to the needed point. Let's consider that now, as you could see, whenever I started again the calculation, whenever I had the results, I had to select again all the configurations. If you use the use configuration over here, then you had results. Whenever we go back, and so, for example, we reduce the interdistance, and in place of 2, we place 1.6, 1.6. We reduce we kept the total number of luminaires, so we reduce the section to 43 luminaires, meters. We go back to the calculation. Once we have the result summary, we can go back and see that now we are 141. So we are now above. And if we select this one, as you can see here, we had already the results. And so simply clicking here, you can see that now we are satisfying the requirements. So we are above the green line. So as you can see, step by step, we can define the lighting of the tunnel. Let's say that this approach can be done automatically. It will be available in a future version of the program. But as you can see, if you like this approach, you may reduce the flux value simply going back to the project and saying that we go back in here, and that's a point, that in here we didn't consider the 0.75 amps, and we stayed at 0.5. But let's say that now we want to reduce, and in place of having a flux of this one, we reduce the flux, because we may also input the flux. We reduce the flux, let's say, to 16,000. And if we place 16,000, this is not possible because it is the lower value. So 0.5, it is corresponding to 19, and we reduce let's say 10%, we go down to 19,000, for example, and we confirm, and okay, and we do it again with this one, and we place 19. Okay. Once we finished, we go back to the calculation. As you can understand, having the flux and power in function of the driving current feature, it is possible really to develop, like we did with road lighting, to an optimizer that will work for you in an automatic way. It is something that will be available. Now we are exactly at the level. And closing this window without selecting anymore, we simply come to this point, or we simply come to this point. So as you can see, it was done manually, but step by step, we can define the lighting of our tunnel. Thank you very much. So have a nice day. Bye-bye.